Good day and welcome to the Math Salon. I'm Dr. Anumende. We are going to look at paper 1, a mix of paper 1 and paper 2 questions for the advanced levels on complex numbers. So the first question says, given two complex numbers, z1 and z2, where z1 is root of 3 plus 2i and z2 is 1 minus I root 3, express z1 divided by z2 in the form a plus ib, where a and b are real numbers. We know you already learned that a complex number, what is complex about it, I don't know. It's just that we want to incorporate all numbers together, can be expressed in the form a plus ib. This is only true if this one is a real number and this one is a real number. So these are all real numbers. But then z expressed in this form is a complex number here. So it means we have to try to express this ratio into this form. So let me just try to write it. So I have z1 divided by z2, but z1 is given as the root of 3 plus 2i divided by 1 minus I root 3. See, mathematics is very beautiful. When I have a whole number, I put I behind. When I have this type of I put here. It makes it look nice. That's why we come to the math salon. So if we look at this, then this is not yet in this form. I would want to express it in this form. So one of the things we can do is that we'll multiply this number by 1. 1 is special. In a salon, one can do so much. So we will choose a special one. A 1 that will be the conjugate of the denominator. Because when a complex number is multiplied by its conjugate, you get a real number. I want that my denominators be real, so I can split it into that form. So what do? I have root 3 plus 2i divided by 1 minus I root 3. This is exactly what is here. And I multiply by 1. But I choose a beautiful one. So 1 plus I root 3 divided by 1 plus I root 3. If you divide this, you get 1. But I want it to be nice. If you put shampoo on here, you won't want to wash it out until it has done the job. So we do that now. We do the cleaning up then. So we try to multiply this out. From here, root 3 times 1 is root 3. Root 3 times I root 3. Root 3 times root 3 becomes 3, because that is root 3 squared. The square removes the root. So I get here plus 3i. Then I take this. 2i times 1 is plus 2i. 2i times I root 3. The I times I is I squared. You must have already learned that minus 1 is equal to I. So if I square both sides of this, then this is I squared, and then the square root here, remove that and I get minus 1. So this I times this I becomes minus 1. So this is minus 1, 2 root 3. Minus 2 root 3 divided by, if I do a similar thing here, 1 times 1 is 1 plus minus I root 3, or let me just first finish with this. 1 times I root 3 is I root 3. Minus 1 times this, minus I root 3 times 1 is minus I root 3. And minus I root 3 times minus I root 3, root 3 times root 3 is root 3 squared, so it remains 3. Minus I times I is minus I squared. So if I multiply both sides by minus, I get minus I squared. So this becomes plus. So minus I squared is plus 1. So it means that I get, in that case, just plus 3. So minus I times I is plus 1. Root 3 times root 3 is root 3 squared, which is 3. So this is plus 3. You see, this one goes off with that. I can put like terms together here. I have root 3 here, and I have minus 2 of the root 3 here. 1 mango, minus 2. So you have minus 1. Minus root 3 here. 2i. 3i plus 2i is 5. You have 5i there, divided by 1 plus 3 is 4. So I can split that out to be minus root 3 on 4 plus 5 on 4i. And I have it in the form a plus ib. If you want, you can put I in front. So then I have it in the form then. Let's see the second one. Given the complex number z is equal to this, find the argument of z. A complex number can always be sketched. If I consider this as the real axis and as the imaginary, then a complex number is how many units to go in the real direction and how many units in the imaginary direction. And this is the angle that we can look for. This angle is obtained as the argument of the complex number z. So my z is given as minus I root 3 plus 1. I will write it as 1 plus, or now minus I root 3. Because the argument, if z is given as a plus ib, then the argument of z is the arc sine to the tangent inverse, or the angle is corresponding to b divided by a. So I'll try to apply. You have to make sure that if they play with you like they did here to put this ahead, you don't make the mistake. You arrange it in such a way that you have the real part here and the imaginary part this way. So if this is the case, then my argument of z based on this problem in hand is tan inverse of minus root 3 divided by 1. Minus root 3, you see the I doesn't come into play. You just pick the part that is here. This is the imaginary part, this is the real part. This is what identifies the part that's imaginary. If you do this, you actually get minus pi on 3 or 5 pi on 6. Because this angle, I think for our particular case, if you draw it, is going to be down here. So you either get minus pi on 3 or you go all around to this point, which gives you the other side. The next question says, find the quadratic equation with one root given by this. Normally we know that we can only get quadratic equations when we have two roots, but that is when the roots are real. If the roots are imaginary, like this case here, it means one is enough, because roots for quadratic equations always appear in conjugate pairs if they are imaginary. That means x is equal to 3 minus I is a root. X is equal to 3 plus I is also a root, where I just change the sign of the imaginary part. So this is the conjugate pair of that one. So we say x1 that. So either x is equal to 3 minus 1i or 3 plus I. But we know that to write the equation, quadratic equation given the roots, is simply x squared minus sum of roots x plus product of roots equal to 0. So I'm just left to look for the sum of the roots. I've said that these two would be the roots. So if I sum them, maybe we call this alpha and beta the way we know it. So if I sum alpha and beta here, alpha plus beta is equal to 3 plus 3, 6, minus I plus I disappears. So I have 6. So this is x squared minus 6x. Then I need the product of the roots. So I have to multiply that. So alpha beta is equal to 3 minus I times 3 plus I. If you do this properly, 3 times 3 is 9. 3 times I is plus 3i. Minus I times 3 is minus 3i. And minus I times I is minus I squared. Minus I squared is 1. So this is plus 1. This one disappears. I have 9 plus 1, which is 10. Plus 10 is equal to 0. So that's a quadratic equation with a root given as 3 minus I. Thank you. And most especially, do not forget to give us some thumbs up, subscribe, share with your friends, and make sure that you keep on checking for new videos. Bye.